Welcome back to the series of lectures on high-performance scientific computing. In the last class, we had started talking about parallelization of problems involving stencils, especially trying to solve partial differential equations. We had said that the global data structure of a particular problem could look something similar to this, where we are trying to evaluate some sort of a differential equation which is evaluated at every point which is represented by the black dot. The stencil method essentially gathers data from its neighbors and does some sort of processing based on the method of discretization, and then solves this problem in some sort of a matrix equation AU is equal to F. Now, obviously this requires communication between the neighbors. Usually these problems end up becoming quite large, such that it is now needed to sort of partition them and distribute them across different processors or different machines so that they can be computed effectively. Typically, what happens is that we try to decompose this mesh into equal sized work pieces. In this case, we have done a simple geometric decomposition of the problem into 9 parts. We have assumed that the size of this problem is equal to n, which is the global size, and we are assuming it to be a square, such as it is an n by n problem. We have px number of processes in the x direction, py number of processes in the y direction, and we are assuming that n is an integer multiple of px and is also an integer multiple of py, such that when we take the n unknowns and divided it among px or py, we get a modulus of 0. We then use some sort of geometric technique to figure out where I am in the global sense of things, figure out what my global offset is. We have some sort of control mechanism to say that, okay, I am process 0, process 1, process 2 in the first row, process 3, 4 and 5 in the second row, process 6, 7 and 8 in the third row. We will notice that process 4 communicates with 4 other processes, process 3 and process 5 communicate with 3 other processes, process 2 and process 7 also communicate with 3 other processes, and the other processes all communicate with only 2 processes. There are some processes which lie on the global boundary of the problem and will have fewer communication points. Now, the question is, how do I go about setting up these communication pairs? So, I use my geometric knowledge in this sense. So, what are all the necessary data transfers that need to be done? So, let us take an example of the center division over here, which I had denoted and said that this could be process 4. Remember that the assignment of process 4 is based on certain logic that I have used. You could use a different logic for yourself. For example, another way of arranging these things could be 0, 1, 2, 3, 4, 5, 6, 7 and 8, 8 being the center process. I have chosen a row by row process because that's easier for me to implement geometrically. Now, for this particular process, when I want to compute something unknown at a point which is on the top row, 3 of the information points usually lie within. But there's one row from which I need information which is not local to this processor at all, and it lies on the processor which is connected on top over here. Similarly, for the bottom row, for the stencil computation, I will need information from the neighbor below. For the right row, I will need it from the right side. For the left row, I would need it from the left side. So, these pseudo interprocessor boundaries will start behaving as some sort of a boundary condition where I need information from the neighbor. In reality, for the physical problem, this is an internal point, but from a computational perspective, this becomes a process boundary. So I need to set up communication pairs between all these processor edges per se. So I need to take data from here and push it to the right side. Similarly, I need to take the data from the right and bring it to the left. I have to do this for all possible pairs of interprocess boundaries. So when we need to do that, we need to allocate data for this at each of these processors as well. And this is where, if you look at each of these unknowns, now let us assume that n was clearly divisible by the number of processors nx and ny. The actual size of the local problem will then be bx and by, and being equal sized, each of these processes, all of them have the same bx and by. So what we would do is we would allocate something called as a halo around this local array, which are these yellow points where the data information interchange needs to take place. So you will have an array which is of the allocated size bx plus 2 multiplied by 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 2. So this yellow bit of data is going to be used for communication from the different sides of the particular process patch. So if I look at the process patch through a halo exchange, and remember, if this is for a 5-point stencil. By 5-point stencil, what do I mean? Is that for any particular point over here, I need information from 4 neighboring points and the 5th point being itself. Now, if I had a larger stencil, so that means I could have an 8-point stencil, I could have a 12-point stencil which is taking more and more information from the neighbors as well. I could have stencils which are not taking data uniformly from one particular direction. All this comes down to the kind of numerical method that you choose to use, right? Here we are using a very simple equally weighted 5-point stencil where the information comes uniformly from all sides. So if I need to have a 5-point stencil, I need to have all these halos. Now let us focus on what we have denoted earlier as process 4 in my numbering system, and we see that this particular green layer, which is on the boundary, the interprocess boundary, now is taken in internally and you have a halo of yellow. This yellow top row communicates with the black row of its neighbor. Data is being exchanged from the black row and copied into this yellow row. Similarly, the data is being copied from this particular black row to this yellow row, this black row to this yellow row, and this black row to this yellow row. So this way, all the pairwise communication is now done, and the information the green boundary bits need to do the 5-point stencil calculation is now readily available locally, and the computation can be done. Similarly, if I were to look at the boundary subdivisions, the yellow row over here, or rather the yellow column over here, requires information from this particular green column, which needs to be copied over towards the left. Similarly, this green column needs to be copied into this particular yellow column over here. The top green column over here will be copied into the bottom yellow, the top green row will now be copied into the bottom green yellow row over here. The bottom green row over here will be copied into the top yellow row over here. So this is done to provide the remote data through some halo exchange. All of these pairwise communications have to be complete, and only then one can go to some sort of a next iteration, and there has to be synchronization for all this communication to be complete. But while the communication is going on, the compute need not stop. You could start computing things in the internal points and then finally come and do the calculations of the boundary once the communication is complete. This is what we meant by overlapping communications and computations, and this is what we meant by use of non-blocking sends and receives, where the computation can go ahead once the send has started, and that can take place asynchronously, and you can do the internal computations while the data is awaited from the neighbor over the interconnect. So what are the different data types that can be transferred between these different arrays or different portions? So remember, I can make these calculations using different data types: floating point numbers, double precision numbers, integers, so on and so forth. When I am transferring this data, we transfer whole chunks of memory. Remember, when we did the MPI send, we sent it to the start point of the address and then said, please take a contiguous bit of memory of certain n elements. In this case, it will be bx or by, depending on whether you're sending the data vertically up or down or horizontally to the sides. So you will need to provide the start point of the particular memory location and the number of items and also the size of each item. So what are the predefined data types that are already available for data transfer? We have the C integer, whose equivalent data type in MPI is MPI underscore int. You have the C floating point number, which is MPI underscore float. The C double precision number, which is MPI double. C unsigned integer of 32 bytes length, that's MPI uint 32. For Fortran, you'll have to use MPI underscore integer to say that it is a Fortran integer. You can also create your own data types or have more complicated data types like structures, vectors, struct, and some other convenient stuff like subarrays. So far we have looked at regular domain decomposition, which was for a nice shaped square or any such regular shape. What if our problem is irregular? How do we do irregular domain decomposition? Now, more often than not, you will end up with problems which are highly irregular in nature, where the domain decomposition will not be easily done using geometric principles. So now let us look at an example of such a complicated irregular domain. Here is a domain which involves a sphere which is embedded right inside over here over a very unstructured and also an anisotropic grid. What do I mean by an anisotropic grid is that the fundamental element sizes are changing dramatically from one geometric location to another geometric location, i.e. the mesh is not uniformly spaced. The mesh also contains irregularly shaped tetrahedra. So you have many elements at the center where there is a small sphere which has been meshed, and as the mesh is taken away from the center of the sphere, it becomes coarser and coarser, giving more and more geometric spacing. From a computational perspective, it does not matter what is the volume of this tetrahedra or what is the volume of the finest tetrahedra. The computer just sees it as a singular point or a data point where some computation needs to be done. So the computational load of a large tetrahedron and a small tetrahedra is roughly the same. So when we have to distribute this problem, if we were to take a simple geometric approach where we just divided it based on Cartesian methods, like just applying slices of planes in x, y, or z direction, we will end up with a very uneven distribution of cells. So you will have a lot more cells towards the center of these partitions and fewer cells in domains, subdomains which are away from each other. That would result in a fairly uneven computing load, which would result in very varied timing, and you will get terrible performance. So the main idea is here, when I partition this mesh, each of these subdomains, which are now in this problem colored by different colors such as yellow, red, blue, and green, i.e. there are 4 subprocesses, the aim should be that each of these subprocesses get the same number of degrees of freedom, or in this problem, the same number of tetrahedra. Now this looks like a challenging problem when it is completely unstructured like this, because there is no geometric principle by which I can easily cut this problem in a way that the number of tetrahedra in the blue zone is approximately same as that of in the red zone. Remember, in this problem we might not get an exactly uniform load ever, because we choose the number of MPI processes at runtime. It could be some integer n. The problem size could have some integer m, which is obviously larger, much larger than n. But there is no guarantee that m is perfectly divisible by n. So when we partition this problem, it's quite possible that we have slightly uneven distributions, but we want to minimize these distributions as much as possible. So how does one even begin to distribute these problems? Thankfully, there are nice sophisticated algorithms and packages which allow us to distribute this problem. The mathematics of doing the perfect cuts is a different science altogether, which requires a course in linear optimization, which we will not be covering in this course. But we will discuss one particular package metis which allows us to distribute this problem equally, or rather roughly equally, amongst different MPI processes. So how do you represent such a complicated problem in the first place so that I can now start the process of sort of distributing it evenly? I represent this sort of a mesh using what is called as a connected graph. Looking at the previous problem, each of the tetrahedral volumes is represented by a vertex in this graph, and each of its neighbors is represented by an edge or a connection. Now, maximally a tetrahedron can be connected to 4 other tetrahedra, so it could have maximum of 4 connections. If you are at the boundary, you could have fewer connections than that. Now, it is quite possible that if you have arbitrary polyhedra instead of just tetrahedra, the number of edges that you are, or rather the number of other vertices that you are connected, could rise even greater than 4, and theoretically it could be infinite. This is particularly true if you are looking at arbitrary graph problems from computer science, especially if you are looking at problems of how people are connected to each other. Let's say that you're looking at a problem of connecting graphs of people on some platform such as Facebook. I could have about 50 friends on Facebook. That means I'm connected to 50 other people. Some person who is probably more popular than me could be connected to as much as 500 people. So in a connected graph sense, I will have 50 edges radiating away from my vertex, and the popular person will probably have 500 edges radiating away from his or her vertex. Now, I can represent the entire mesh or the system as this connected graph. I can also assign weights to these edges or other preferential connections. Now, if I were to look at the example from Facebook or any social media platform, I would say, okay, if number 3 is very good friends with number 1, I will assign it a higher weight, maybe 2, or maybe 3 is even a stronger friend, in theories alluding to the fact that 5 is a stronger friend with 3 compared to 1 over here. So similarly, you could build what is called as a weighted graph by assigning edges weights. Now, from a perspective of computational fluid dynamics, this could represent edges where the surface area is most or surface area is least. It could represent edges where gradients are more or gradients are least. That depends on the nature of problem that you're trying to solve. Now, the idea here is that I want to take these graphs and sort of distribute them in such a way that the number of vertices in each of the subgraphs are approximately the same. So how do I partition this particular graph? That means I have to cut these edges. So I will cut these edges in a manner such that once I cut these edges, they become distinct graphs on their own, or they become subgraphs, and each of these subgraphs have what is called as roughly the same number of vertices. But there's a second optimization problem that I would like to do as well. I would like to cut it in a way that I cut the minimum number of edges. That means if I cut the minimum number of edges, that means I'm cutting the minimum amount of communication pairs or communication points. So my communication load between the two processes will be at a minimum if I minimize the edge cuts. If we have certain preferences of edge cuts, then I would use a weighted graph. For example, if I look at the left side graph, there is no information about the relationship of 3 with 1 and the relationship of 3 with 5. But in the weighted graph, we have some more information. And in this graph, when I am doing the edge cuts, I would much rather cut the edge between 1 and 3 than the edge between 3 and 5, because I think 3 and 5 is more important because it has a higher weight. So you want to minimize the weights on the cut graph or the cut edges. So this is a mesh representation of connected graphs, and you can take any complicated mesh and represent it as a series of graphs. How do I represent this graph from a visual structure to actually a data structure or an array? For this, we have the compressed storage format or the CSR format, where we have the adjacency structure of the graph stored. The CSR format is typically used for storing sparse graphs. Let me go back to the original domain over here, which is made up of completely tetrahedrons. Now let us assume that this particular problem has 1 million tetrahedra. We can now represent the connectivity between each of these 1 million tetrahedra using an n by n matrix. But we know that each tetrahedra is connected at the maximum with 4 other tetrahedra if it were an internal tetrahedron. The reason being, a tetrahedron has only 4 faces, right? So a lot of these connectivities in an n by n matrix representation would actually end up being zeros, or it is what is essentially a very sparse matrix. So this would require a vast amount of memory allocation, which is wasted because a lot of the entries are essentially just 0. Instead, we can use this compressed storage format, which makes it very efficient to store these large sparse graphs. So in this format, let us assume that you have n vertices or n elements or n degrees of freedoms, and these n vertices are connected via m edges. M is the total number of edges in the entire system, not just at each vertex. Now we can represent this using just 2 arrays. One is called XADG, the other one is called adjacency. Now XADG is an array of size n plus 1, where n plus 1 is, n is the total number of vertices that we have, and the adjacency array is basically of size 2m, because we have an edge from vertex v to vertex u, and similarly we have another edge, one directional edge from vertex u to vertex v. So each actual edge is represented by a pair vu and uv. So hence we have 2m, the size to be of adjacency array. So if I look at this simple graph over here, let us say that now this is a fairly regular mesh. We have 5 points in the x direction and 3 points in the y direction, and we have numbered them sequentially from 0 through 14. Now remember, we can do a simple geometric decomposition of this problem by giving 5 points each to each of 3 processes. But what we would like to do is first store it in the CSR format and then use any sort of generalized principle of decomposing the data. So we see here that 0 is now connected to 5, 0 is connected to 1, 0 is connected to 0 is not connected to 6, 0 is only connected to 1 and 5. Whereas the first vertex is connected to 0, 1 and 6. So all the vertices are either connected to 2, 3 or 4 other vertices. So, each of these vertex, the 0th vertex is given x edges, this is the start point of the pointer of the adjacency vector. So, if I take the difference for the first point, or rather point number 2, which is denoted as ID 1, and I take the difference between 2 minus 0, it gives me the number of connections the first point, which is 0, has. And it also tells me where does the connections for point number 1 begin. So, if you look at it, 0 has 2 connections, which is 2 minus 0, and the 2 connections are 1 and 5. Similarly, 1 has connections 5 minus 2, that is 3 connections, and the connections are 0, 2 and 6. So, they begin at adjacency 2. This is adjacency 0, this is adjacency 1, this is adjacency 2. This is the start point of the connections of the x adjacency 1, and there are 3 connections which are 0, 2 and 6. So, similarly, if you keep on going over here, you can reconstruct this whole graph just using these two vectors. So, this reduces my data consumption dramatically from n square to n plus 1 plus 2m. So, you can now see that there is a fairly complicated piston cylinder arrangement, which is an engineering problem which has been completely decomposed by this particular library Metis, which now uses the CSR graph as an input and can go ahead and decompose this computational domain over a fairly complicated geometry like an automotive engine cylinder. This was done by a PhD student, Sandeep Menon, in 2011. In the next class, we will now start looking at some simple examples of MPI programming and also how to do domain decomposition in MPI. Thank you.